So, hello everybody. I am Bryce Adelstein Lelbach. I am a principal architect at NVIDIA, where I work on HPC and quantum computing programming models. I'm also the chair of the Standard C++ Library Evolution Group, and I'm the chair of the US Programming Languages Committee. Before all of those lofty titles, I worked at Louisiana State University on a parallel runtime called HPX. And so my background, my roots are sort of in parallel programming. And so it's very exciting to me to be talking about parallel programming in standard C++, which is what we're going to be doing today. So first, a few conventions that I'm going to use throughout these slides in the interest of brevity. Like my predecessor Titus, I really strongly dislike nested namespaces in the standard library, so I'm just going to use these namespace aliases instead. So std_v for std views, std_r for std ranges, and ex for std execution, and then this thread for std this thread. I'm also going to make liberal use of class template argument deduction. So standard C++ has always supported the deduction of template arguments when you're calling a template function. But in C++ 17, we extended this to work for class templates when calling their constructors. So for example, when constructing a tuple, I don't need to spell out what the types are. They can just be inferred from the arguments. Likewise, if I'm constructing a std array, the element type and the size can be inferred. So I'm just going to use that throughout the entire slide because it makes my code a little bit shorter, which means I can make it bigger so it's easier to read. All right, so the barrier to entry for parallel programming today is far too high. We live in a world where almost all hardware platforms are parallel and require explicit programming to utilize that parallelism. Despite that, many users and many code bases do not utilize parallelism. And for those that do, many have chosen approaches that are not portable to accelerators such as GPUs. And that really sucks for all of you because, like, today it's just GPUs, but let me tell you, like, coming down the line, there's like all these other accelerators that you're going to have to use in your applications if you want to get performance. Like Moore's law is over. The future is accelerators. Like NVIDIA, we have GPUs, but we also have these things called DPUs. And as I mentioned at the front of this talk, part of my mandate at NVIDIA now includes quantum computing. Stay tuned to my Twitter if you want to learn more about that. So it's really important that we have portable parallel programming solutions which can allow users to express parallelism that'll work across a variety of platforms. So the C++ committee wants to build sort of an on-ramp to parallel programming. We want to give users easy-to-adopt solutions that will give you good enough performance on most of the platforms. Obviously, something that's portable is not going to always be able to expose all of the capabilities of every single individual hardware platform. But we want to give you something that's going to be enough to get you started. And then maybe where you really have a really key performance need in one particular part of your application, maybe there you'll have to go to some platform-specific extensions. But the idea is that parallelism in the C++ standard will get you onto the parallel programming highway. And then that makes it easier for you to switch over to using something like CUDA C++ or OpenMP. So there's three basic pillars to our strategy for parallelism in standard C++. First, we need a corpus of common algorithms that dispatch to vendor-optimized parallel libraries. Next, we need tools to allow you to write your own generic parallel algorithms that can run anywhere. And then finally, we need mechanisms for composing parallel invocations into task graphs for essentially asynchronous programming. So let's start with that first pillar, the collection of common parallel algorithms. So C++ has had a set of serial algorithms for manipulating sequences of objects since the first standard. We're all familiar with these, for each, accumulate, etc. These algorithms all operate on one-dimensional sequences. Initially, they were parameterized with iterators, but with C++ 20, we've introduced a new, more powerful abstraction, ranges. There's about 100 different standard C++ algorithms. We have for loop abstractions, filters, sorts, searches, rotations, reductions, scans, etc. Now, in C++ 17, we introduced parallel versions of these algorithms. And the parallel overloads have the same interface as their serial counterparts, except that they take an additional parameter, an execution policy, which describes what form of parallelism is allowed, if any. Execution policies essentially describe the how of execution, but they don't specify the where. That's left entirely up to the implementation. So execution policy parallelism could be implemented with a variety of different strategies. It could be some bespoke CPU thread pool, could be OpenMP, or it could be GPU acceleration. So there's 4 execution policies in the standard. There's seek, which indicates that all operations must be performed within the calling thread and must be indeterminately sequenced. So basically it says that you're not allowed to have any parallelism here. Then there's unseek, which also requires all operations to be performed in the calling thread, but allows those operations to be unsequenced with respect to each other, which means that vectorization is allowed but not required, but not parallelism. Then there's par, which allows implementations to parallelize operations at its discretion. It doesn't require parallelism, it just says you can parallelize this if you want to. But it also requires that all the operations within each thread are indeterminately sequenced, which means that vectorization is not allowed. And then we have par unseek, which allows operations to occur in multiple threads and to be unsequenced with respect to each other, which means that both thread and vector parallelism is permitted. And again, this means parallelism and vectorization are allowed, but they're not required. The implementation may choose to not parallelize. Like if you call a parallel sort with a single element, most implementations are probably not going to go and do anything in parallel for that, or even for a small number of elements like 8 or so. So let me show you one of my favorite parallel algorithm examples, a parallel word count. So we're going to have this word count function. It's going to take a string view. And we can write this with a single parallel transform reduce. So transform reduce takes both a transformation operation and a reduction operation, and it applies the transformation to the inputs, which creates this sort of pseudo sequence. And then it uses the reduction operation to sum the results of those transformations. If you're familiar with MapReduce, this is C++'s form of it. So we're going to use the overload of transform reduce that takes 2 input sequences and a binary transform function. So the first input sequence is going to be the entire string except the last element. And the second input sequence will be the entire string except the first element. And so this is sort of like a stenciled operation here. So our binary transform function will be passed a window of every 2 adjacent characters in the string. So our transformation function's job here is going to be to tell us whether the 2 adjacent characters that it's looking at are at the beginning of a word. If the left character is white space and the right character is not white space, then the right character is the beginning of a word. And the pseudo sequence that's going to be produced by this transformation is going to look like this. For every word, one and only one invocation of that transformation function is going to return true. But what about that first character of the string? We never actually test it with our transformation function. We start at the second character. So we account for that first character in the initial value of the reduction. So our reduction operator here is just going to be plus, because we've got this pseudo sequence where there's a 1 true value for every word. So we just have to sum them up, and that'll give us how many words are in the string. And so that's going to give us the answer. And so this is, standard C++ code. It's parallel and portable. You can use it on MSVC. You can use it with GCC, with the Intel compiler, with the NVIDIA compiler. You can run it on a CPU and a GPU. And yeah, I really like this little example. Okay, so in C++20, the standard library introduced ranges. And unlike iterators, ranges are designed from the ground up to be composable. Ranges allow us to express a wide range of algorithms in terms of a few different key primitives. Now, of course, C++20 is after C++17 when we introduced the parallel algorithms, and we did not introduce parallel range algorithms yet. However, you can still use the C++20 ranges in conjunction with C++17 parallel algorithms to do some quite powerful things. So standard C++ algorithms typically iterate over sequences of objects, for example, the elements of a container. But sometimes we want to iterate through indices instead of objects. This is particularly important in numeric and scientific computing. So we can do this using iota, a range factory that was introduced in C++20. So it produces a range of monotonically increasing integers. For example, iota 1 to n is going to give you a range of all the integers from 1 to n minus 1. If you're familiar with Python's range, this is the same thing. So instead of passing iterators to a container to a parallel for each, we can instead pass an iota range, which gives us a parallel for over the indices instead of the objects. We can also use this in conjunction with another range view, Cartesian product, to iterate through multidimensional index spaces. So C++23 is adding Cartesian product, which is a range adapter that takes multiple input ranges and produces a range of all the ordered tuples formed by taking an element from each one of the inputs. So when we take a Cartesian product of some iota views, that's going to give us all of the ordered tuples in some multidimensional space here. And so here we're using this to write a pretty simple parallel matrix transpose using the C++17 parallel algorithms. So the range V here is going to produce the two element tuples from 0, 0 to n minus 1, m minus 1. And the iteration order here is going to be row major. The second index is going to be the contiguous one. We can change to column major by switching the order of arguments to Cartesian product and the order in which we unpack them from the Cartesian product sequence. So the C++17 parallel algorithms have another limitation, which is that they're fork join synchronous. So each invocation launches its work in isolation in blocks until that work has completed. So for example, if we invoke two parallel for eaches on the same data back to back, we're going to get two parallel work launches. The caller is going to be blocked waiting for the first invocation to finish, and only then, after that's finished, will it go and launch the second invocation, and then go and wait for that one to complete. And this transfer of control back to the caller is a latency bubble, and it can degrade performance, especially if the place where you're running this in parallel has a little bit longer latency to talk to, like, for example, a GPU. So one way that we can address this problem is to fuse those two operations together into a single parallel invocation, which we can do with the transform range adapter. So transform takes an input range and a function, and it returns a range that is the result of applying that function to the input. And this is done completely lazily. So the function is only evaluated as needed when the elements of the returned range are accessed. So for example here, f is not evaluated until the elements of v are accessed within the parallel for loop here. Now there is, of course, one big change in semantics here, which is that previously we had a guarantee that all invocations of f would happen before any invocations of g. And so we no longer have such a barrier if we do this sort of fusing here. But in a lot of cases, you don't actually care about that semantic. You just sort of like structurally want to do a bunch of operations at once, and it's fine if they're fused together. So another useful range adapter is filter, which takes an input range and a predicate function and produces a range of all elements of the input for which the predicate returns true. And again, this is done lazily. So the predicate isn't evaluated until the elements of the return range are accessed. So here we're going to use filter in combination with a parallel reduction to sum only the positive elements of a container. All right, so now I'm going to show you some example applications that have already adopted standard C++ parallelism. So Lulesh is an HPC mini app for Lagrangian explicit hydrodynamics on an unstructured grid. So it's designed to stress vectorization, parallel overheads, and on-node parallelism. And it's been ported to a variety of different parallel programming frameworks like MPI, OpenMP, OpenACC, CUDA, and now also standard C++. And with the standard C++ version of Lulesh, you can get performance that matches many of the other backends, but writing just regular standard C++ code. And that same code will compile with a variety of different compilers, GCC, NVCC, Intel, the MSVC compiler, and it can run on either a CPU or a GPU or some other accelerator if you have a compiler that can do that. So another example is STLBM, which is a lattice-Boltzmann framework written from the ground up in standard C++. It can run on multi-core CPUs and GPUs without any code changes. It doesn't use any language extensions or external libraries or vendor-specific code annotations or pre-compilation steps. It's just standard C++, which I think is pretty exciting. And just using the standard C++ code, we can run it on parallel on a CPU or on parallel on a GPU and get the same performance that we would have if we'd written 2 versions of that code, 1 for each platform. So another example, Maya, which is a code space for aerospace flow and noise simulation, which has been ported to C++ standard parallelism. And again, here we have the same effect where you can take the same standard C++ code and run it on a variety of different platforms using a variety of different compilers. Okay, so I hopefully have convinced you that the C++ parallel algorithms that we introduced in C++ 17 are great, but they're really just the start of the story. I sort of pointed out a few of the limitations that they have, and we'll talk a little bit more about those limitations and what we plan to do about them throughout the rest of this talk. So there's really 2 major limitations. The first one is that the C++ 17 parallel algorithms are all fork join synchronous. So they launch the parallel work, and then they wait until that work has completed before they return to the caller. Now, where exactly do they launch the parallel work? And that's the other limitation, that by design, users have no control or visibility into where the parallel work runs. It just happens on some amorphous implementation-defined execution context. It might be a CPU thread pool or a GPU stream or Grand Central Dispatch or Windows fibers, et cetera. You don't really know. It's going to be whatever your implementation decides to do, including your implementation may just decide, I'm just not going to parallelize this at all. And so implementations have complete freedom here, and users have no control other than saying this could be parallelized implementation if you so chose to do so. So today, we don't really have a standard model for asynchrony, and we have no way to express where things should actually execute in the C++ standard library. But fortunately, the solution is coming soon to your C++ implementation, which is the senders and receivers framework, which is an asynchronous execution paradigm for standard C++. So let's take a look at a simple example here. Okay, so first we need to get a scheduler from somewhere. This could be a thread pool, it could be a tasking system, a GPU driver, et cetera. And then once we have that scheduler, we want to start a chain of work on it, the scheduler. And we do that by calling schedule, which is going to return a sender. And that sender will complete on the execution context associated with the scheduler. So next we're going to use a sender algorithm called the then to compose work onto the sender that we got from the scheduler. And this work will be performed on the same execution context. And that sender algorithm is going to return a new sender, which we can use to add more work onto the chain. And then finally, we're going to wait for the chain of work to complete using sync wait, which will return the value sent by the final sender in the chain. So there are 3 key concepts in this senders receivers world. First, we've got schedulers, which are handles to execution contexts. And schedulers produce senders. Then we have senders, and those represent asynchronous work that will eventually send some signal. And they can be composed together using sender algorithms, very much in the same way that ranges can be composed together using range algorithms. And you can form task graphs that way. And then finally, we have receivers, which process asynchronous signals sent by senders. So if you're familiar with the future promise paradigm that's used in a lot of C++ code bases, senders are sort of an abstraction and generalization of futures, and receivers are sort of an abstraction and generalization of promises. All right, so let's talk about schedulers in a little bit more detail. So I said that they're handles to execution contexts, but what exactly does that mean? So an execution context is a resource that represents the place where execution will happen. So this could be some concrete resource like a specific CPU thread pool or a GPU stream. It could also be something more abstract like the current thread of execution. Execution contexts don't necessarily have a representation in code, and they don't necessarily have an exposed interface, at least today. They may have state associated with them like OS handles, memory, metadata, etc. So schedulers represent a strategy for submitting work to execution contexts. They're lightweight, non-owning handles to contexts. Schedulers are cheap to construct and pass around, and the execution contexts hold all the state. So sort of in the same way that an allocator is just a lightweight handle to a memory resource, a scheduler is just a lightweight handle to some execution context. So multiple schedulers can refer to the same execution context, including multiple different kinds of schedulers. For example, maybe you have one scheduler that will submit work at a high priority to an execution context, and you have another scheduler that will submit work at a lower priority. You might even have a scheduler that dispatches work to multiple different execution contexts. So as I said, schedulers produce senders. We use schedulers to make the senders that will perform work on whatever execution context is associated with the scheduler. And once we've obtained a sender from a scheduler, we can then compose work onto it. And so next, let's look at senders and how we actually compose them together. So as I said before, senders represent asynchronous work. They form the nodes of an asynchronous task graph, which span multiple schedulers and multiple execution contexts. Senders are lazy, so you have to explicitly start them. They do not start executing until they have been started. And when a sender's work completes, it sends a signal to the receiver attached to it. So receivers are handles that get notified with a signal by a sender. And there are 3 different handling paths, which we call channels. The value channel is used to indicate successful completion and may pass 1 or more values to the receiver. The error channel indicates that the sender's work failed and passes an error object that contains information about the failure. And then finally, we have the done channel, which is used to indicate that the sender's work was canceled before it can be performed. This is distinct from the error channel because in this model, cancellation is not an error. It may be something that happens during the course of normal operations. So each sender is going to notify its attached receivers with one signal, meaning only one of these 3 error channels is going, or one of these 3 signal channels is going to be invoked. So now let's take a look at how we actually hook up senders to receivers. So let's start with a scheduler here, which is going to produce some initial sender that we're going to work with. And so then we're going to have a receiver that's going to be attached to this sender, and we do this with connect. This is a behind-the-scenes operation that you're not going to normally see if you're just using senders and receivers. You'd only really see it if you're implementing your own senders. And what connect returns is called an operation state, and that contains the actual work that the sender represents. And eventually, you're going to initiate the work by calling start on the operation state. And then after some time, that operation will complete. And then it will notify the receiver with one of those signals through one of those 3 channels. So next, let's take a look at sender composition itself. So we compose together senders using sender algorithms, and there's a few different forms of them. The first is sender adapters. So sender adapters take 1 or more senders as parameters, and they return a sender. So most sender adapters are pipeable, just like range adapters. The semantics are similar to Unix shells, so send pipe F, pipe G is equivalent to G of F of send. So languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. And this syntax is essential for the elegant composition of senders. So composing senders via nested function calls would be a bit of a mess. The order in which operations would occur would be inverted from the order in which they appear in code. The predecessor senders in this example here are more deeply nested and thus appear after their ancestors, which is a little bit confusing. And things get a bit clearer when we instead use temporary variables to name each stage of the composition. But this can be really error prone because it's easy to mix up one of those named variables. And so that's why we have the pipe syntax, because this gives us a clean way to compose chains of senders in the order that they will be evaluated that's not super error prone, like using a bunch of temporary variables. So let me show you a couple of the most important of the sender adapters. So first there's then, which we've already seen, and that takes an invocable F and calls it with the values sent by the prior sender. The sender returned from then will send the results of that invocation of f. So this is how you attach a continuation to a sender. So bulk is similar to then. It evaluates the invocable once for every index in the shape in. In the simplest and most common cases, the indices are one-dimensional and start at 0, and the shape argument is just an integer indicating how many invocations you want to perform. So the sender returned from bulk is going to pass along the signal that was sent by the prior sender. So it'll just pass through whatever that signal was. So transfer changes the scheduler that's going to be used for the next sender in the chain. It doesn't actually change the scheduler for any of the prior senders. It just says, hey, anything that comes after me, I want it to run on this scheduler. So some senders can only be connected to a single receiver. For example, because they move any values or errors that they send instead of copying them. We call these one-shot senders. Senders that can be connected multiple times, we call them multi-shot senders. And split is a sender adapter that takes any type of sender and returns a multi-shot sender that passes along the signal from the original sender. So split senders represent forks in a sender task graph. So this allows you one way of introducing parallelism by having multiple consumers. Conversely, WinAll takes multiple input senders and returns a single aggregate sender that will send the signals from all of the inputs. Senders that are returned by WinAll don't have any scheduler associated with them that means they don't promise where they complete. And we made that decision because it would be challenging to pick which one of the input senders we should take a scheduler from. So instead, we just make you explicitly request where you want this operation to complete. So WinAll senders represent joins in a sender task graph. WinAll is not a pipeable sender adapter because the partially applied piped form would be ambiguous with the fully applied non-piped form because all of the inputs are senders and it's variadic. So ensure started connects and starts a sender, and it returns a new sender that will pass the signal sent by the original. So if the input sender is a composition containing other senders, those senders will be connected and started as well. So sender factories are another kind of sender algorithm. Unlike sender adapters, they do not take senders as parameters, but they do return a sender. So sender factories are used to start new chains and graphs. The senders they return are the new root nodes of those graphs. So we've already seen one of those, which is schedule, which returns a sender that completes on the specified scheduler. The return sender doesn't send the values or represent any actual work. It's just a handle that you can use to compose more work on that scheduler's execution context. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. So like if you just have like a std vector and you just want to like start a chain that will have that std vector be sent through, you just do just of the std vector. So the last type of sender algorithms are sender consumers. So these take senders, but they do not return senders. So they typically launch a sender graph by connecting it and starting it, and they're the leaf or terminal nodes in sender graphs. So sync wait is a sender consumer, and it's a synchronization primitive that blocks until a sender completes and then returns or throws whatever was sent. The sync wait that you're going to see in most of the examples will be in the std this thread namespace. That's a concrete form of sync wait that uses a blocking mechanism that's suitable for a std thread or the main thread. But we imagine that in the future there may be additional forms of sync wait, such as one that is suitable for use with fibers. Okay, so now I want to dive into some of the details of how these sender graphs actually get formed. So let's suppose that we have a single link in a chain of senders. So we're going to have an abstract before sender adapter on the left-hand side of this link, and then a concrete then an adapter that calls some function f, and then an abstract after adapter on the right-hand side. So if we unroll the pipe syntax, we're going to have something like this. We've got a before sender that came from somewhere, and then we create a then sender which will contain the before sender and the function f. And we're going to also create an after sender, which will contain the then sender. So we're going to end up with a nested structure of senders that'll kind of look like this. At some point, we're going to connect a receiver to the outermost and last sender. Each sender in the nested structure will connect a receiver to its child, and this is going to happen in the opposite order of sender construction. So you sort of walk down the graph one direction, and then you walk back up it when you start attaching receivers. And so that's going to give us this nested receiver structure, which is the inverse of the sender structure. A nested operation state structure is also going to be produced and returned from connect when you call connect here. So eventually we'll start that operation state, and as the operation is complete, they'll begin notifying their receivers with signals. When the before receiver gets its signal, it will notify the then receiver. If it's a value signal, the then receiver is going to invoke F with the value and signal the after receiver with the result of that invocation. So it looks maybe a little bit mind-blowing, and there's a lot of going down graphs, going up graphs, a lot of nesting here, but once you start to wrap your head around it, it is actually quite an elegant model for composition. Okay, so now let's look at a slightly more advanced example. We're going to write a generic asynchronous and parallel inclusive scan. We'll write it as a pipeable sender adapter so that it can be composed with other sender algorithms. So sender adapter here is just some made up wrapper type that turns a lambda into a sender adapter object. So this inclusive scan async is going to take 3 parameters, a sender, which we will expect to send the input as a range, an initial value, and the number of tiles to split the input into. So we're going to use the classic 2-pass parallel scan approach, which requires temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender has sent us the input. So we'll chain a then sender onto the prior sender. In the body of that continuation, we're going to create a vector to hold the partial results. So we'll return both the input range and the vector, which we need to be sent to the next sender in the chain. So next, we need to do the first parallel pass, which is called the down sweep. And so in that pass, we're going to use a bulk to invoke the body of this pass for each one of the tiles. So inside of that bulk, the first thing we need to do is calculate the range of elements that belong to the tile. Then we're going to take all of the elements in each tile, and we're going to perform a local serial inclusive scan on them, which we do right here just by calling std inclusive scan. Okay, next we need to propagate information between the tiles. The sum of each tile needs to be added to the elements of all preceding tiles, sort of like this. So we've already computed that sum. It's the last element of the local inclusive scan that we just did. So we're going to just store that result into the partials vector. And then the assignments to this partials vector, they're going to happen concurrently but from different tiles, but that's perfectly fine because each tile uses a different and unique slot in partials, and nobody reads from partials yet, so there's no data race here. And then at the end of it, we're going to have all those sums in this partials vector. Okay, so then after all the tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial inclusive scan of partials to get the values that we need to propagate back to all of the tiles. And we're going to do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence and the partials vector to the next sender in the chain. So the result of the scan over partials looks like this. The information that each tile needs to add to its elements is in the partials slot for the tile directly preceding it. So now we just need to do the next pass where we go parallel again to distribute that information to all of the tiles. And this is called the upsweep pass. So we're going to pipe another bulk on here, which is once again going to be over all of the tiles. And in the body of this bulk, we need to calculate which elements belong to the current tile, just as we did before. And then we're just going to use a serial for each to increment each element in the tile by the appropriate value from the partials vector. And after that addition, we're going to have the correct result. So finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector. We want the partials vector to go away now because we're done using that storage. We'd like it to be cleaned up. So we're going to add a final then sender, which only passes along the input. And so then the partials vector will be destroyed when this then sender completes. And that's it, we're done. We've got a nice generic asynchronous and parallel inclusive scan that we can run on any scheduler that we want on any platform, and that we can pipe with other sender algorithms. So we can imagine that we'll have a whole set of asynchronous parallel algorithms based on senders and ranges. The design space for these interfaces is still open. It's straightforward for some common cases, like a series of for eaches over the same sequence. We could have an in-place transform async, which takes a sender of a range and a callable and returns a sender of a range. And it's easy to rewrite that series of synchronous for eaches into a lazy asynchronous operation with transform async. But let's look at a more interesting case here, normalizing the elements of a range. And we can do this by getting the maximum element of the range and then dividing each element by that maximum. So it's a bit more challenging to map this to asynchronous execution. The piping syntax is great when you have one dependent value that you want to pass down the chain, such as a single input sequence. But in this case, there are two asynchronous inputs to the second call, the input sequence and the maximum element. So we may want asynchronous parallel algorithms to return richer senders. For example, reductions like max element async should probably send both the input sequence that was passed to it and the iterator to the maximum element. So I want to show you one or two more examples. So we've developed a prototype implementation of the senders and receivers proposal at NVIDIA, and our prototype supports CPU schedulers, GPU schedulers, and distributed schedulers. So we've written a couple different examples with that. This one right here is just a simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. So this is the entire solver loop, which is just expressed as a graph of senders. So we can take this code and it can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler that's passed to the solver, we can go from running inline on a single CPU thread to running in parallel on a CPU using OpenMP, to running on a single GPU, to multiple GPUs within a single node, to multiple nodes scaling up to thousands of GPUs. So with standard C++ senders and receivers, you can, just by changing one line of code, go from a single CPU thread all the way up to a cluster of GPUs. So another application that we've been working with is this framework called Palabos, which is a framework for parallel computational fluid dynamics simulations using the lattice-Boltzmann method. And we've ported one of its applications to senders and receivers. And the simulation, which you can see visualized on the left here, models carbon sequestration techniques. So the porous structure that you see is sandstone, and it is filled with saturated salt water, which is not visible on this representation. And the red bubbles correspond to liquid CO2, which is injected at the bottom and travels through the sandstone because of buoyancy forces. And using our distributed GPU scheduler, we've been able to run this application at scale on up to 512 GPUs, which is pretty exciting for us. So senders and receivers are the next major step in the development of C++ standard parallelism. They deliver the second and third pillar of our plan. The framework gives us the tools that we need to be able to write our own generic parallel algorithms, as we saw earlier, that can run anywhere, and also to compose asynchronous task graphs. So following the standardization of senders and receivers, we'll introduce new asynchronous sender-based versions of the standard parallel algorithms. Now I want to switch focus a little bit and talk about multidimensional programming in C++. So today, C++ doesn't really have any reasonable abstraction for multidimensional data. This is unfortunate because many of the interesting compute-heavy problems that benefit from parallelism have a multidimensional shape. And that's why we're introducing MDSpan, a multidimensional span type in C++23. And I'm very glad this is the first time I've given this talk where I can say with some certainty that it is actually going into C++23. And this is very similar to the one-dimensional span introduced in C++20. So when I joined the committee back in 2015, I joined with the singular goal of standardizing something like this, and it's only taken, nearly a decade. So hopefully it does make it into C++23. So MD-span is non-owning. It's just a handle to some underlying data. It doesn't manage the lifetime of the data, just like span. And also like span, MD-span is cheap to copy. It just contains a pointer and metadata describing the size and shape of the structure. So the metadata, such as the extent of a dimension, can be expressed either at runtime or compile time, allowing for metaprogramming and compile time optimizations, as well as helping out the compiler in doing loop optimizations. MD-span parameterizes how a multidimensional index is mapped to a location in the underlying data. We call this parameter a layout, and it can express any kind of multidimensional structure. There are some concrete layouts in the standard library for the common use cases, but anyone can define their own layout and plug it into an MD-span. Likewise, MD-span parameterizes how it accesses the underlying data. The default is just to perform a normal C++ pointer dereference with an index, but with a custom accessor, you could instead use a special cache bypassing instruction, read from disk, or perform a remote memory access. So MD-span uses extents objects to express the number of dimensions in a space, the rank, and their length, the extents. Extents objects take a variadic number of integrals as template parameters. For dynamically sized extents, the magic value dynamic extent is used as a template parameter, and the extent is passed to the constructor. But through the power of C++20's class template argument deduction, when you're working with all dynamic extents, you usually don't need to spell out the entire verbose instantiation. You can just rely on CTAD. So this E0 example here is equivalent to this E1 example. It's just a whole lot less characters. There's also an alias called dextents for the all dynamic extents case. It takes a single parameter, which is an integral specifying the rank. And that's useful if you need to write a return type where you can't do CTAD, like a return type for a function, for example. For statically sized extents, the extent itself is passed as a template argument, and no corresponding constructor argument is needed. You can also mix static and dynamic extents. For example, in this case, we have one static extent and one dynamic extent. So we'll need to pass just one extent at runtime. Extent objects and MD-span support arbitrary but static rank. So you can have as many dimensions as you want, but you have to know how many dimensions you want at compile time. So MD-span has 4 template parameters, 2 of which are optional. So the first is the element type. The second is the extents type, and this must be a specialization of the extents class template. The third is a layout. The default is layout right, and we're going to discuss layouts more in a few minutes. And then the final parameter is an accessor, which performs the element access. So MD-spans of all dynamic extents have a very simple syntax. With class template argument deduction, you can construct one without specifying any template parameters. If you do need to spell the type out, it's still pretty concise. You just use the dextents alias. And the elements of an MD-span are accessed via the index operator. Thanks to a recent core language change in C++23, the index operator can now take multiple parameters, which is really nice. So we don't have to use the call operator here. We can use the correct operator. You can also make MD-spans of static or mixed extents. The simplest way to construct these is by passing an extents object as the second constructor argument and then relying on CTAD. So now let's talk a little bit more about layouts and how they work. So the 2 most common layouts are layout right and layout left. So with layout right, the rightmost extent is contiguous, meaning that its stride is 1, and the strides increase from right to left as the product of extents. So this is the layout for C++ built-in arrays and for NumPy. It's also the default for MD-span. For example, if we had a 2x2 matrix, the 2 elements on the first row would have data locations 0 and 1, and the elements on the second row would have data locations 2 and 3. So with layout left, the leftmost extent is contiguous, meaning its stride is 1, and the strides increase from left to right as a product of extents. So this is the layout that's used by Fortran arrays and by MATLAB, and the layout that's very common in scientific and HPC computing. So if we had a 2x2 matrix in layout left, the two elements in the first column would have data location 0 and 1. And the two elements in the second column would have data location 2 and 3. There's also a standard layout that allows you to explicitly specify the strides for each extent. That's called layout stride. So all three of the concrete layouts that are in the standard library are just implementations of a layout concept. Generically, a layout is just something that maps a multidimensional index to a data location. Anyone can define a layout. Layouts may be non-contiguous. They may map multiple indices to the same location. They may perform complicated or expensive computations. And they may have or refer to state, although we generally advise against that because that will start to break down some of the assumptions that people will make about MD spans being cheap to copy around and being non-owning. So the parameterizing layout is critical because it allows us to write generic multidimensional algorithms that can be used with any layout. And this can be an essential component of portability because different layouts may be needed on different platforms to deliver on performance. Today, we have a bit of a vocabulary problem with multidimensional types in the C++ ecosystem. Suppose I write a function that uses a concrete owning multidimensional type like eigenmatrix. Eigen is a popular library for matrices and matrix algebra. So my users will be able to pass an eigenmatrix to this function. But what if we have a boost UBLAS matrix or a PppOnSea matrix or a Blaze matrix or a cutlass tensor or a multidimensional array that's been passed to us from Fortran, et cetera, et cetera. That's where MDSpan comes in. By using it in your interfaces, your code can work with any multidimensional data structure. Because MDSpan is just a non-owning handle, you can construct one that refers to any type of matrix, an eigenmatrix, a boost UBLAS matrix, a PppOnSea matrix, a Blaze matrix, a cutlass tensor, yada, yada, yada. So for example, suppose we had our own row major matrix class like this. We can just add a simple MDSpan conversion operator to this, allowing us to pass our matrix class to any interface that expects an MDSpan. In some more complex cases, we might have to write our own layout type, but in a lot of cases, you'll just be able to use the concrete ones that are in the standard library. So now let's take a look at some examples of how we can use MDSpan. So first here, we've got a simple 3D 7-point stencil interkernel, similar to what you'd see in some HPC proxy applications like MiniGhost. And we have two 3D MDSpans here representing the problem state. And we're going to use this Cartesian product of iotas technique that I showed you earlier to create a range that iterates the multidimensional index space. And then we'll use a parallel for each to iterate through that space. If we want to change the layout, all we have to do is change the input MDSpans. Everything else will remain the same. So earlier, I showed you this example of a simple parallel matrix transpose. We used span and dealt with the multidimensional indexing manually. That's not particularly portable. We've hard-coded a specific data layout, which may not make sense in all circumstances. It's also error-prone, as it's easy to make a mistake in the indexing formula. So we can improve this by using MDSpan instead. So now we can change layout by simply changing the type of MDSpan that we use. I'm fairly happy with that last slide, but I really want more down the road. I'd like to have something like this. And there's three things here that we don't actually have yet. First of all, we don't have parallel algorithm overloads that accept ranges directly instead of iterator pairs. Second, I'd like to have some sort of indices method on MDSpan that returns a range of its multidimensional index space. And in fact, I'd like to have some form of iteration for MDSpan, because you may have noticed I've not talked about iterators for MDSpan because it doesn't have them right now. And if you're interested in learning more about that, come to or watch my C++ North talk, which is currently advertised as just being another version of this talk, but will actually be a talk where we go into detail of the challenging problem of multidimensional iterators. And then the third thing that I really want here is a language extension to allow me to destructure tuples in lambda parameters, because I hate having to just put this as like the first line of the lambda. It drives me nuts. So going a step further, what I really want is I want an asynchronous version of this that parameterizes where it runs. Like this is the sort of code that I would like to be able to write in the future. This is parameterized on the data layout, and it's parameterized on where it's going to run, and it's asynchronous in parallel, which is great. So MDSpan has a powerful slicing interface with an unfortunate name, sub-MDSpan. This takes an MDSpan and returns a sliced MDSpan. So because MDSpan is non-owning and cheap to copy, slicing is also cheap. You're just creating a new view of the same underlying data. The input MDSpan is not modified. So for each extent of the MDSpan, you pass a slice specifier to sub-MDSpan. And there are 3 different kinds of slice specifiers. So you can specify a single index to be selected for an extent by passing an integral as a slice specifier. And the rank of the returned MDSpan is reduced by 1 for each single index slice specifier, because you're sort of slicing away that entire dimension. You can also pass a range of contiguous indices to be selected for an extent. And then finally, you can pass this special value full extent to select the entire extent. So for example, here we have a 3D MDSpan M0, and we make a slice of it by selecting 8 indices for each extent, starting at indices 16, 32, and 8 respectively. So the MDSpan returned by sub-MDSpan M1 is going to have a rank of 3 because we didn't use any single index slice specifiers, which would have caused a rank reduction. And each of the extents of M1 will be 8. And the multidimensional indices for M1 will be offset from what they would be for M0. So for example, M1 0, 0, 0 would be equal to M0 16, 32, 8. So let's look at another example, this time with rank reduction. So we'll slice M0 selecting the index 16 for the first extent, the entire second extent, and index 32 for the third extent. So the MDSpan that we will produce, M2, will have rank 1. And the extent of that rank will be 128, which is the extent of the second dimension of M0, which we selected the entirety of. And iterating this 1D slice will be equivalent to accessing M0 with a fixed index for the first and third extent. So sub-MDSpan is a pretty useful tool for writing tiled algorithms. So let's look at building a tiled version of the parallel matrix transpose that we looked at earlier. We're going to work with square tiles with extent t by t. So first we need a range describing the set of all tiles. And again, we're going to use that Cartesian product of iotas technique for that. And it's okay if the tiles are at the edges extend beyond the bounds of the matrices. We're going to fix that up in a minute. So then we're going to have a parallel for each. And this time it's going to iterate over the tiles, not all of the indices. And for each tile, we're going to create a new sliced MDSpan for A and B using sub-MDSpan. First, we need to determine what range of indices we need to select based on the coordinates of the tile. And this is where we're going to handle tiles that would go beyond the bounds of the matrices. We just truncate them to the end of the matrix. And so now we'll pass the tuples describing the indices we want to sub-MDSpan, producing the local MDSpans for this tile. And then next, we need a range of multidimensional indices within the tile. Again, we'll use the Cartesian product of iota for this. And then finally, we use a C++ range-based for loop to serially iterate over the indices of the tile and perform the transpose with the local MDSpan slices that we've made. And with that, we're done. And again, if you want to see more of this, watch my talk at C++ North. It gets a lot cooler from here. All right, so the set of standard C++ algorithms that we have today is pretty great, but it's not complete. What we have is primarily focused on manipulating one-dimensional sequences of objects. We only have a very limited set of numeric algorithms, such as reductions and scans. We don't want C++ programmers writing their own versions of common numerical algorithms like matrix, multiplication, etc. We want them to use standard interfaces that are designed by that are backed by an implementation, that are designed and optimized for whatever platform they're running on. And so the C++ committee is exploring new families of algorithms to standardize in this space, starting with linear algebra. So we don't want to reinvent numerical linear algebra on the committee. We just want to standardize existing practice. And the existing practice for linear algebra is BLAS, the basic linear algebra subprograms. So we just want to create a modern C++ interface that can be implemented under the hood by existing BLAS libraries. So the existing one-dimensional C++ algorithms parameterize data with iterators and since C++20 ranges. For standard C++ linear algebra algorithms, which are two-dimensional, we plan to parameterize them instead with MD-spans. We use the MD-span parameter to express things that appear as distinct parameters in traditional C-style BLAS interfaces. So for example, instead of having scaling parameters on matrix vector product, we have a scaled operation that takes a scaling factor in an MD-span and returns a new MD-span that will apply the scaling factor upon access. C++ standard library implementations can see through this abstraction, of course, and extract the scaling factor to feed it to a lower level BLAS interface that expects it. Another example is transposed, which returns a transposed version of the supplied MD-span, and again does this lazily and upon access. As with today's C++ algorithms, we're planning to have serial and fork join execution policy parallel overloads of the linear algebra algorithms. In this example here, where we solve a system via upper triangular Cholesky factorization, we'd want to chain together these two operations and launch them asynchronously. And so we imagine that in the future, we'll have asynchronous sender adapter forms of these algorithms that will allow you to do just that. So there's plenty of other work down the road for C++ standard parallelism. There's other classes of numerical algorithms. There's asynchronous streams. There's various memory model extensions and concurrency primitives that we should be adding. There's affinity and locality facilities. But I think with every standard revision, we are delivering more and more components of C++'s story for parallelism. And I think it's starting to shape up into a pretty good story. So I want to end where we started with our goal, which is that we need on-ramps to parallelism in standard C++. Almost all platforms today are parallel, yet a shocking amount of code does not take advantage of that parallelism. So we want to normalize parallelism and accelerated computing. Writing parallel C++ code should be easy and natural. Parallelism should be something that we do by default, not something that we have to explicitly think about or opt into.